Okay, let's really dig into this. Picture this. You walk into your office, maybe it's just a regular Tuesday, but outside, it's not good. Could be a crazy heat wave, like 105 degrees, and you're hearing news about the power grid straining. Or maybe worse, the sky's got that eerie orange glow from wildfires miles away, and the air quality, forget about it, it's way off the charts. For a long time, when we talked about high-performance buildings, it was pretty much all about saving energy, being green. But things have changed. Our climate, public health scares, it's reshaped what we need from buildings. Now it's really about, well, survival, protection. So today we're doing a deep dive into how construction is having to adapt. Like right now, we're focusing on a really key part of the new LEED V5 standard that's leadership in energy and environmental design, specifically a credit called EQc4, Resilient Indoor Environmental Quality. And this is where the building codes get serious about what happens when the outside world, fails.
That's exactly it. The source materials we're looking at, they spell out the technical nuts and bolts that are driving this shift. Our mission today is to unpack these detailed standards. We want to show you how new buildings are essentially being required to plan ahead to make sure people inside stay safe and healthy, even when facing, extreme climate events or health threats. We're basically decoding the engineering behind real, measurable building resilience.
Okay, and before we jump into all those fascinating details as the specific rules, how you score points for this stuff, if you're the kind of person who loves understanding how complex systems work, especially the ones that shape our daily lives, then make sure you hit subscribe right now. You'll get more deep dives just like this one, exploring the infrastructure around us. All right, so let's start with the big picture. The why behind all this. The language in this EQc4 credit is pretty striking. It talks about supporting design features that increase the capacity for occupants to adapt to changing climate conditions. That word, adaptation, instead of just efficiency. That feels like a major shift, doesn't it?
Oh, absolutely. It's a fundamental pivot. The standard is basically saying, look, we know these risks are coming. We're already seeing them. So you have to build that knowledge into the design from day one. Architects, engineers, they can't just assume stable weather and, power that never goes out. The documents we have are explicit. This credit is designed to protect people from events that may compromise the quality of the indoor environment and subsequently occupant health and well-being. It's like the building industry is formally acknowledging, okay, these extreme events could be terrible air quality from fires far away, could be another pandemic, could be heat waves knocking out power. They're not freak occurrences anymore. They're becoming part of the baseline. Core design challenges. The building itself has to be sort of a last line of defense, a safe haven when things outside get chaotic.
And it's not like you have to do everything at once, right?
Yeah.
The sources mentioned you can get up to 2 points under the LE New Construction Standard, version 5, and you get those points by picking different options to address different threats. So it's kind of modular.
Exactly. That modular approach is key because, let's face it, the biggest risks aren't the same everywhere. If you're building in California, wildfire smoke might be your top priority. Somewhere else, maybe it's extreme cold snaps or hurricanes. But the core requirement is still there. You have to prove through design documents, through modeling, through actual testing during commissioning, that you've seriously tackled at least one major threat to the people inside. It really shifts the burden. It's not just about showing energy models anymore. It's about demonstrating survivability.
Okay, so that sets the stage. We understand the why. Now let's get into the how. Starting with these active management modes, the system's designed to react quickly, right? These first two options, they're about the building systems being, well, smart, responsive. They need hardware and controls that can actually change how the building operates based on immediate, real-time threats from outside, like active defense. And the sources are clear. These specific options apply to new construction projects. Okay, option 1 first. This one's worth a point, and it tackles bad air coming from outside. The main example they give is wildfire smoke, which makes total sense given recent years. But it also covers other varying outdoor conditions or events that mess with indoor air quality, the IAQ. We've all seen those pictures, right? Major cities just choked in smoke. This standard aims to make sure that inside the building, you can still breathe safely.
Yeah, this is a direct response to what's happening with climate change. It's becoming a necessity. If you're putting up a new building in an area prone to fires, you can't just rely on the standard AC filter anymore. The system itself needs what they call an episodic outdoor event management mode. And what gives this teeth, what makes EV5 powerful here, is that it doesn't just state the goal. It ties it directly to a really specific, tough technical standard. eShare Guideline 44. eShare, as you probably know, is the big authority on heating, ventilation, and air conditioning. Guideline 44 is all about protecting people indoors from high levels of outdoor particulate matter, that nasty fine dust and smoke particles.
Okay, so ASHE Guideline 44, what does that actually mean for the building's design? What does a builder have to install or change? Are we talking serious hardware?
Oh yeah, definitely. We're talking significant upgrades. First off, the filtration gets beefed up considerably. Your typical office might use, say, a MERV 8 or maybe RV 11 filter. Guideline 44 often pushes that up to MERV 16 or even higher. These are filters designed to catch the really tiny, dangerous particles, the PM 2.5 stuff. And second, it requires sophisticated controls. The system needs to be able to automatically sense when outside air quality tanks and then quickly reduce or even completely shut off the fresh air intake. Sometimes this means the building has to switch into a kind of lockdown mode, slightly pressurizing the inside to keep polluted air from seeping in through cracks.
Wow, okay. That dynamic switching, reducing air intake, pressurizing, that sounds complex to actually get right and test. You can't just, like, draw it on a plan and hope for the best. And the standard says this mode has to be included and verified in the design docs and, crucially, during commissioning.
That commissioning piece, that's where the rubber really meets the road. It's the real cost, but it's also the real guarantee of resilience. Commissioning for a smoke protection mode isn't just checking if the right filter is installed. It's a serious performance test. It often involves simulating an event, maybe with detailed computer modeling, or sometimes even physical smoke tests outside the building to measure how the building reacts under pressure. They have to physically verify things like, do all the outside air dampers seal completely shut? Does the building maintain that slight positive pressure to keep smoke out? And most importantly, do the indoor air quality sensors confirm that the PM 2.5 levels inside stay below the safe threshold, even while the system is in this emergency mode? It's way more involved, more complex, and frankly, more expensive than just signing off on a standard HVAC system. It forces the design team to prove it works when it absolutely has to.
Okay, that makes sense. It's about proof, not just promises. Now, moving to the second option, option 2. This one also offers a point, but it shifts focus. Instead of bad air outside, like smoke, it's looking at dangers inside, specifically airborne biological stuff. This seems like a very clear response to the COVID-19 pandemic, right? Requiring buildings to have an infection risk management mode.
Absolutely. And this part really shows how these building standards are getting much more technical and specific. The sources lay out a very precise requirement. This special mode has to provide the minimum equivalent clean airflow rates specified in HHRI 241-2023, Section 5.1.
Okay, equivalent clean airflow rates, or ECA. You said that's a game changer. Why is that different or better than just saying you need X number of air changes per hour, like the old way?
It's a really big deal because it moves towards measuring the outcome genuinely clean air rather than just the input, like how much outside air you bring in. Traditional air changes per hour, or ECH, just tells you how often the volume of air in a space is replaced. ECA, equivalent clean airflow, is different. It measures the total effectiveness of all your air cleaning strategies put together in removing contaminants. So, and this is really key for understanding the innovation here. The standard actually encourages and gives credit for using things other than just flooding the space with outside air. You can hit those required ECA rates by using, say, super high efficiency filters internally, like HEPA filters, or, and this is important, by using technologies like UVGI, that's ultraviolet germicidal irradiation. UVGI systems use UV light inside the ductwork or in upper room fixtures to actively kill or deactivate airborne viruses and bacteria as the air circulates. So if your fancy filter or your UVGI system can clean the internal air just as effectively as bringing in the specified amount of fresh outside air, according to AHRA 241, then you comply. It opens the door for more efficient and innovative ways to deal with airborne pathogens.
Ah, I see. So instead of forcing a building in, say, Minnesota to heat up huge amounts of freezing winter air just to meet an air change number, you mandate the result clean, safe air and let them use smarter tech like UV to achieve it.
Exactly. It's performance-based. You achieve the required level of cleanliness however you get there most effectively. But just like the smoke mode, the proof is everything. You don't just get to say you have UV. You need to document the whole strategy, the design philosophy, how the system switches into this infection control mode, what the expected performance is. All laid out according to ASHRA 241's documentation rules, section B10.2, and then it has to be verified during commissioning. They have to measure and prove that the system delivers the promised equivalent clean airflow. It takes the guesswork out of pandemic readiness for building operators and ultimately protects the people inside.
Okay, very thorough. So we've covered the active systems, smart filtration for smoke, advanced cleaning for germs. But what about the scenario where everything just stops? The power grid goes down. Maybe the air outside is fine, but there's no electricity, no AC, no heat, nothing. This is where option 3 comes in, focusing on passive resilience, how the building itself keeps people safe. And this one could be worth 1 or 2 points.
Yeah, this section is, in some ways, the most fundamental shift. It forces everyone involved to think about the building's basic structure, the walls, the roof, the windows, as a life support system. Can it keep people alive without any help from mechanical systems?
And the test scenario they use is pretty brutal, isn't it? The sources say you have to model a power outage lasting 2 full days, 48 hours straight, during the absolute worst conditions expected in a typical year. And you prove compliance using thermal modeling software. That term, TMY, typical meteorological year, sounds technical. What does that actually represent? Why use that specific data?
Right, TMY isn't just the single hottest or coldest day ever recorded in a location. That would be almost impossible to design for passively. A TMY dataset is more sophisticated. It's built from many years, sometimes decades, of historical weather data for a specific place. It pieces together a full year's worth of hourly data points, temperature, humidity, solar radiation, wind speed that are statistically typical for that location. But crucially, it includes the typical extreme conditions. So it represents the kind of really hot summer day or really cold winter night that you can reasonably expect to happen regularly, not a once-in-a-century event. And modeling a 48-hour power outage against that TMY data is tough because you can't rely on any short-term tricks. The building has to maintain survivable temperatures for 2 solid days using only its inherent properties. The model has to prove the envelope, the insulation, the windows, the thermal mass is good enough to buffer the inside from those extreme outdoor temperatures for that entire time with zero energy input.
Okay, so let's break down the 2 paths within option 3. Path 1 is about extreme heat. 1 point for this.
Correct. For Path 1, the requirement is that the building must passively maintain what they call thermally habitable conditions during that simulated 2-day peak summer power outage, which is, frankly, a huge ask.
Thermally habitable for 48 hours without AC. Wow. That means the building materials have to do all the work. We're talking serious insulation, like high R values in the walls and roof. Probably special reflective roofing materials, maybe strategically placed concrete or phase change materials inside to absorb heat. And definitely high-performance windows, double or even triple paned with special coatings to keep the sun's heat out.
Absolutely. You're essentially designing the building to act like a giant, very efficient thermos. And this leads to a really important concept mentioned in the sources, designating specific thermal safety zones.
Ah, right. Why only zones? Why not require the entire building to stay habitable?
It mostly comes down to practicality and cost. Trying to passively keep an entire large office building or hospital cool enough for 48 hours during a peak heat wave, the amount of insulation and specialized materials needed could become astronomically expensive. By allowing designers to designate specific, often smaller, areas as thermal safety zones, maybe interior core spaces, lower floors away from the hot roof, areas with extra thermal mass, they can concentrate the resilience efforts and the associated costs. The idea is if a prolonged outage hits during extreme heat, people would move to these pre-identified zones where the temperature is guaranteed by the design and modeling to stay below a dangerous threshold, often something like 86 degrees Fahrenheit or 30 Celsius, to prevent heat stroke. It's a targeted survival plan.
Makes sense, a practical compromise. Okay, so path 2 is the flip side. Extreme cold. Also worth 1 point.
Yep, similar requirement, but for the deep freeze. During the simulated 2-day peak winter power outage, the building has to passively maintain thermally habitable conditions. Here, the physics challenge flips. It's all about stopping heat from leaking out. So the focus is on extreme air tightness, sealing every little gap, plus massive amounts of insulation, and paying very careful attention to thermal bridging. Thermal bridges are those weak spots where heat can easily escape, like where steel beams connect through insulation. You have to minimize those relentlessly. The goal is to trap any residual heat inside from people, maybe leftover warmth from equipment, any sunlight coming in, and prevent the indoor temperature from plummeting into the danger zone for hypothermia, usually defined as staying above something like 40 or 45 degrees Fahrenheit, around 4 or 5 Celsius.
And the sources point out an interesting alternative way to comply with this cold weather path. If a project achieves Passive House certification, LEED BD+C automatically considers it to meet this requirement. That seems like a big deal.
It's huge because passive house is arguably the most rigorous building standard in the world when it comes to airtightness and insulation performance. It's incredibly demanding. So LEED is essentially saying, look, if you've managed to meet the full passive house standard, we trust that your building envelope is already good enough to handle a 48-hour winter power outage. This can save a project team a lot of time and effort on separate thermal modeling if they're already going for passive house certification anyway. But whether you do the detailed modeling or use the passive house route, the sources emphasize that for both the heat and the cold paths, you still have to designate those specific thermal safety zones. That requirement remains.
Okay, this brings up something I was wondering about. We're talking about making buildings super airtight for this passive survival option, right? Option 3, lots of insulation, ceiling leaks. But earlier, for option 2, the infection control mode, we were talking about needing potentially huge amounts of ventilation, bringing in clean air or using systems like UVGI, following ASHRE 241. Aren't those two goals, super airtightness and high ventilation, kind of fighting each other?
That's a fantastic question, and it gets right to the heart of the challenge in modern, truly high-performance building design. You've hit the nail on the head. They can be conflicting goals. To survive passively, option 3, you want to seal the building up like a thermos. To fight airborne disease, option 2, you need robust air exchange or cleaning. The solution lies in having both capabilities and very smart controls. The key is energy recovery ventilators, or ERVs, sometimes called heat recovery ventilators, HRVs. These devices are essential. When the building is running normally, or even in the high ventilation infection control mode, the ERV system preconditions the incoming fresh air using the energy from the outgoing stale air. So in winter, it warms up the cold incoming air, and in summer, it pre-cools and dehumidifies the hot, humid incoming air. This drastically cuts the energy penalty of bringing in lots of outside air needed for option 2 compliance. Then the control system needs to be sophisticated enough to manage these different modes. Normal operation uses the ERV for efficiency. Infection control mode might prioritize maximum clean airflow via the ERV and supplemental cleaning like UV, accepting a temporary energy hit for safety. And then, if the power fails completely, option 3 scenario, the airtight envelope takes over for passive survival. The ERV wouldn't be running then, obviously. So the airtight shell helps when the grid is down, but you need the mechanical systems with energy recovery to handle ventilation when the grid is on. It's about having layers of capability, all verified through commissioning.
Got it. So it's about designing for multiple scenarios and having the systems and the airtightness to handle each one. The puck's guys. All right, we've covered the high-tech active systems and the robust passive envelope. Now we get to the final piece, option 4. And this one feels almost old-fashioned. Operable windows.
Simple, maybe, but incredibly important for resilience. You're right, it seems low-tech compared to ASHRE 241 or thermal modeling. But think about those situations that aren't total grid collapse or citywide smoke events. What if just the AC unit for your floor breaks down on a hot day? Or a localized power flicker knocks out the ventilation temporarily? If the air outside is actually okay, being able to simply open a window provides a vital manual backup for ventilation and cooling. It gives occupants some control when the automated systems fail. It prevents a space from quickly becoming stuffy or dangerously hot due to a localized issue.
Okay, and how does LED incentivize this? The sources mention scoring tiers based on how many spaces get these windows.
Right, it encourages widespread use. You get 1 point if you design at least 50% of the regularly occupied spaces with operable windows. But you can aim higher. If you manage to provide operable windows in 75% of those spaces, you earn a full 2 points.
2 points just for windows seems generous, but I guess it reflects their importance as a backup.
Exactly. LE is rewarding that commitment to providing a simple, reliable, non-powered way for occupants to manage their immediate environment if the main systems go offline or if they just want fresh air when conditions allow. If 3/4 of your building can get basic ventilation manually, that significantly lowers the risk when things go partially wrong.
But knowing LE, they probably don't just let you put in any tiny window that barely opens, right? There must be technical stacks.
You guessed it. No token windows allowed. The sources are clear. The operable windows have to meet specific requirements for opening size and location laid out in ASHRA 62.1 2022, Section 6.4.
ASHRA 62.1. That's the main ventilation standard, isn't it?
Yeah.
So what does Section 6.4 likely demand?
Precisely. Referencing 62.1 ensures these windows are genuinely functional for ventilation. That section deals with natural ventilation calculations. It means the window's openable area usually has to be a certain minimum percentage of the floor area. It serves often around 4% or more. Tiny slot windows won't cut it. Plus, there are often rules about placement, how far the opening is from occupants, ensuring it can actually create meaningful airflow, ideally facilitating cross-ventilation by having openings on different sides of a space. It forces designers to integrate reasonably sized, well-positioned, operable windows that can actually make a difference, not just tick a box.
Okay, so we have the high-tech dynamic air cleaning, the super insulated passive survival shell, and the low-tech but properly specified window backup. Seems like it covers the main bases for failure.
It really does try to create a layered defense. It acknowledges that different things can go wrong: bad air outside, disease inside, total power loss, localized system failure, and provides distinct strategies for each. You've got mechanical systems backed by standards like ASHRE 44 and 241 when the power is on. You've got the building envelope itself, proven through modeling when the power is off. And you've got basic manual control via Windows as another fallback. It really raises the bar from just building efficiently to building for genuine safety and health security under stress.
Right, that was a lot to unpack, but it paints a clear picture of where high-performance building design is heading.
Yeah.
So let's just quickly recap those 4 key areas of resilience we covered from ADV5 EQc4, just to tie it all together. First, we have the active systems dealing with air quality issues. That was active management for outdoor pollutants needing compliance with ARI IGAR Guideline 44 for things like smoke. And second, active management for internal biological hazards, demanding that infection risk mode meet ARI 241-2023's equivalent clean airflow rates, possibly using things like UVGI. Then we shifted to the building itself as the defense. Third was passive thermal safety, using TMY data modeling to ensure the building can keep designated zones habitable during a 48-hour power outage, whether it's extreme heat or cold. And finally, the fourth layer, the backup. Operable windows needing to cover 50% or 75% of spaces and meet functional requirements from ASHRE 62.1.
And stepping back, looking at the whole picture, the big message here from LEEV5 is that the definition of a high-performance building has fundamentally evolved. We've moved past just optimizing energy use or using nice materials. Now it's about hard, quantifiable, verifiable measures of survivability, of health security, of adaptability to a world that's proving to be pretty unpredictable. These requirements are forcing the industry to bake resilience into the design from the very beginning, to treat potential disasters not as fringe possibilities, but as predictable challenges that the building must be designed to withstand. It's setting a completely new benchmark for how buildings need to protect us. It acknowledges the environment outside is changing, sometimes becoming actively dangerous. The next generation of top-tier buildings, the LEV5 certified ones, will have had to prove through rigorous testing and commissioning that they can provide a safe haven, breathable air, tolerable temperatures, even when the grid fails or the air outside is toxic.
Absolutely fascinating and frankly essential stuff. This is just one specific credit in one standard, but it shows the direction things are moving. If breaking down these kinds of complex systems and standards is something you find valuable for understanding the world being built around us, definitely make sure you're subscribed so you don't miss our future deep dives.
And maybe here's a final thought to leave you with, something to chew on as you look at the buildings you use every day. If brand new construction is now being required to invest heavily in design, materials, and modeling just to prove it can keep people passively safe for only 48 hours without power, what does that imply about the level of risk we're accepting in all the older buildings, the ones that were never designed with this kind of resilience in mind? Especially as those climate extremes, the heat waves, the cold snaps, the poor air quality events become less extreme and more, well, normal. Something to think about regarding the resilience, or lack thereof, in the structures that surround us right now.